Kirchhoff's circuit laws.
If you're watching this video, you're probably familiar with Ohm's law, with potential dividers, and you can calculate for simple circuits currents and potential differences. Now, Kirchhoff circuit laws are actually used to calculate more complex circuits, to calculate the currents and the potential differences. The IB limits this to just two source-carrying loops, so quite simple. You might even be able to solve this with what you know so far, but just to understand how Kirchhoff circuit laws would be applied, we're going to have a look at one example here so that you can calculate, in this case, currents, potential differences. You could just then calculate based on that using Ohm's law. So let's have a look at how you would do these and how you would actually apply Kirchhoff circuit laws. In this example here, I want to calculate the different currents that I have in my system. So let's say I have a current, let's say I have a current I1, I have a current I2, and I have a current I3. The direction of the currents does not matter. You just get a negative value if the actual direction of the current is in the opposite direction. Now, if you look at different videos on Kirchhoff circuit laws, there are different rules that you find. What I find the simplest is what I'm going to show you here, and that is so totally sufficient for what you need to know. As discussed previously, for your cells, you always have the long line representing the positive and the short line representing the negative. So these two would be my longer lines. What you want to do is start your loop always from the positive terminal. So my first loop, I'm going to go around the loop in this direction here. I'll call this Roman 1. So if I want to set up my first equation for this, I would say 10 equals, so positive 10, because I'm starting from the positive, and then I'm going around, and here I'm going to go against current I1, and there's no resistor in this first section of this loop, so I can ignore that. And then I have I3 times 3 ohms, or I can write it as 3I3. I'm putting it here to the right because I have I1, I2, I3, and I want them in the right order. It makes it easier for me when I enter the numbers on the calculator on my GDC to solve the simultaneous equations. Now down here, for the 4 ohm resistor, I would have the current going in this direction because it's the same I1 that flows out of the battery at the top, which also has to flow into the battery, flows into the battery at the top and flows out of the battery at the bottom, according to my arrow that I drew. So for I1, I get 4I1, but because I'm going against the direction of the current, as it says here in the second rule, count IR as positive if the direction of the current and loop are aligned. Here they're not aligned, so I need to write it down as a negative loop. For my second loop, I could just do this, but just for demonstration purposes, I'm actually going to do something different, and I'm going to do the following. I'm going to go around the loop like this. You can pick these large loops. There's no problem at all with that. Now, as we do that, and I'll call this Roman 2, as we do that, I have, again, my 10 volts here, but if you look, there's a second source now in my loop, and I need to put the sum of the EMFs on the left. However, if you were to move this 5 volt source towards the 10 volt source, and let me draw that here, you see that I'm leaving the positive end of the first source, and then I'm facing the positive end of the 5 volt source. This is like putting the cells into your torch. well, when you have like a 3-cell torch and you put one of them the wrong way around, your your torch will probably not come on or be very weak. So the result of this is that you don't add the EMFs, but you actually need to subtract the 5 volts. So overall, I'm just getting 5 volts rather than 15. If the orientation was the other way around, needless to say, of course, I would have to add them up. So, having said that, let's move on. I have now 2I2, and if I look at the direction, I'm going against I2, so this is a negative result. And then I have I1 here, and it's negative 4I1. And I3 is not part of this second equation at all, actually. And now I want the third equation, because I have 3 unknowns, so I need 3 equations. And the junction rule always allows for a simple solution. I can figure this out quite quickly. The junction rule is about conservation of charge. Conservation of charge means that whatever current goes into my junction, whatever rate of flow of charge goes into my junction has to come out. So what comes out is I1 and I3. Can't see that properly anymore. Here it's there. I1 and I3 come out of this junction and I2 goes into it. So that means that I2 is actually equal to I1 plus I3. I want to write this in the same format as the other equations. So I'm putting 0 on the left, bringing I2 over to the right, and then I have I1 minus I2 plus I3. So it's 1 I1 minus 1 I2 plus I3. Okay, now I have 3 simultaneous equations that I can just enter into my GDC and solve them that way. So what you see here is that I have some coefficient times x, another coefficient times y, another coefficient times z, and that is equal to dn. D in my case is my potential difference, or EMF rather. So I have 10 here, 5 for the second one, and 0 for the last row. So these are all fine. For my first value, I have negative 4 I1, that's correct. I2 doesn't feature, so 0 is the right number, and then it's 3. For the next line, I have negative 4 I1, and then negative 2 I2, and I3 doesn't feature, so 0. And for the last line, the values are correct as well. So I want to solve this, pressing F1, and these are the values that I get. So they are my answers that I get for the application of Kirchhoff's circuit laws to this circuit that I have here. Thanks for watching.